Okay, thank you. Okay, so good morning, everyone. So today we're going to continue our discussion of the interaction diagrams and where the case where you have a combined axial force, compression force, and moment. Okay. So what we discussed last time is as the the moment or the eccentricity increases, okay, the capacity of the column regarding the normal force is going to decrease to account for the added capacity for the moment, okay. And this is called the interaction diagram, which gives you the capacity, the Pn, the nominal capacity for the axial and bending moment for a given section. The eccentricity is measured from the plastic centroid of the column. So what's the plastic centroid? It's the point where the axial force, when the axial force is applied, it will give uniform strain, okay, at failure. So now, today, we're going to try to hopefully solve two examples, okay? The first example is on how to locate the plastic centroid of the column, okay? And the second example is how to construct this interaction diagram by plotting or finding those points, okay? So let's start with the first example, trying to find the plastic centroid. So by definition, what's the plastic centroid? It's the point over which, if the axial force is applied, the strain distribution will be uniform, okay? So that's the first example that we want to solve today on locating the plastic centroid. So that's example 10.1. This is on locating the plastic centroid for a given section. So in that example, we have a section that looks like this. It's a T section, column that looks like a T column. And over here there are 4 steel bars in this column. The dimensions, this is over here is 3 inches and 3 inches, and then this part over here, this is 3 inches and this is 5 inches, and then for the other side over here, this is 4 inches and 8 inches and 4 inches. Okay. The location of the steel on the, here, how much is the cover from this side? Well, it's symmetric. It's not given, but it's symmetric. There is a stirrup over here. Okay. As you see here in this example, okay, we have this column and we're required to find the plastic centroid. To find the centroid, I just need to give you the section, okay? But to find the plastic centroid, okay, you need to know the material property, okay? Like, for example, this section has steel and concrete, so what's the strength of the steel and what's the strength of the concrete to find the plastic centroid? Because the centroid is different from the plastic centroid. To find the centroid of a shape, that's you learn how to do this in statics. The plastic centroid, the definition of the plastic centroid is different. The plastic centroid is the location of the point over which, if the axial load is applied, you're going to have uniform strain. So it's related to the forces, okay? So here you need to have, okay, the properties here. So FC prime for the concrete here is 4 KSI, and F yield for the steel, you have grade 60, so F yield is 60 KSI. the steel that we have over here, those are 4 number 9 bars, okay? And we're required to locate the plastic centroid for the shown section. So to solve this problem, what do we know? We know the definition of the plastic centroid. The plastic centroid is the point over which the strain is uniform. At failure, how much is that uniform strain, the magnitude of that uniform strain? 0.003. So at failure, the strain distribution is uniform everywhere. The strain, this is the strain distribution. It's 0.003 everywhere. It's negative, it's compression. So if you have a uniform strain like this, how will the stress look like? How much? You have two different materials here, concrete and steel. If you have the strain of 0.003, how much is the stress in the concrete will be? 0.85 FC prime, the maximum strain, stress, right? Because the strain here is the failure strain, so the stress is going to be the maximum stress, okay, in the concrete, 0.85 FC prime. In the steel, how much is the stress in the steel will be? Fu, right? Because the strain is 0.003, which is larger than epsilon yield, right? Epsilon yield is 0.00207, so the steel here yields. So you know that the material, the strain, the stress distribution in the concrete, okay, since the strain is uniform and equal to 0.003, therefore the stress in the concrete is uniform as well and equal 0.85 FC prime, and the stress in the steel is Fu. Okay? Now, on this section, there are forces, okay, that gives you this strain distribution. There is an axial force, right? The location of that axial force that gives you this strain distribution is the location of the plastic centroid, okay? So, if you have an axis of symmetry over here, the neutral or the plastic centroid will act on that axis of symmetry. So the plastic centroid acts on this line because it's symmetric, okay? But with regard to the horizontal distance, you don't know where's the plastic centroid, right? That's what we want to find. So here there is a point over which, if the load is applied, it will give you this strain distribution, okay? Where's that point? That's what we're looking for. This distance, let's call it x bar, okay? So we're looking for that point, x bar, over which, if the axial force is applied, you're going to have this strain distribution. How much is that axial force? And what's its location? We're going to do those, find the location and that axial force in 2 steps. So first, this strain gives you a uniform stress. The stress multiplied by the area will give you the force in each part. So I'm just going to divide my section into 3 parts because those are the components of my section over here, okay? So let me copy this. And paste it here. So the stirrups here will not play, a role in the solution of this problem, I'm going to divide my section into an A1 and an area 2. Those are what? Concrete or steel? Those are concrete, okay? So A1 and A2 are concrete, and I have the steel here. Okay? So each of those parts has a force, right? So let's find those forces. First, are those forces tensile forces or compression forces? Compression, right? It's an axial compression force, okay? We're not dealing with tension forces. Concrete is not good in, resisting a tensile force. If it's a tensile force for a column like this, then use steel. Don't use, concrete. Concrete is not a good option here. So C1, okay, is the compression force in A1. C2 is the compression force in A2, and CS is the compression force in the area steel of that column. Okay? How much is C1? That's easy. You should tell me how much is C1.
The area times 0.03.
The force is equal to stress multiplied by area. How much is the stress? No, that's the strain. 0.85 FC prime. So it's 0.85 FC prime multiplied by A1. So it's 0.85 times 4 KSI multiplied by A1. How much is A1? It's 6 inches multiplied by 16 inches. So C1 is 326.4 K. How much is C2? Okay, so 0.85 FC prime A2. So 0.85 times 4 KSI times A2, which is 8 inches. The width over here is 8 inches, multiplied by the thickness, which is 8 inches as well. So C2 is 217.6 K. How much is CS? The compression force in the steel. The same formula that we used over here. What's that formula? What does this formula say? The force is equal to stress times the area. What's the stress in the steel? F yield. Okay? Multiplied by the area. The area of 4 number 9 bars. The area of the steel. Those 4 number 9 bars gives you an area steel of 4 inches squared. So that's multiplied by area steel. Now, if I calculate this compression force in the steel, does this give the forces in the section, those 3 forces, or there is tiny small mistake that I did here? Okay, what's that mistake?
I don't want to.
Okay. This area, this orange area, I'm counting it twice now, right? I'm counting it with the concrete, and I'm counting it with the steel. Is that correct? No, it's not concrete, it's only steel. So I should deduct this area from the concrete here, right? I didn't. So I will deduct it while calculating this C steel, compression force in the steel. So how much is the force? How much was the force here if this was concrete? It's this area steel multiplied by the stress in the concrete. So now I should subtract this from this force. So it's F yield area steel, right? And then I subtract 0.85 FC prime area steel. Is this part clear, or do you want me to explain it in another way? Why I'm subtracting this? Okay? So someone would say, okay, why didn't you subtract it from here? Because when I subtract it from this part, I'm subtracting it from its correct location. Okay? If I subtract it from this part, okay, it might not be in the correct location. Maybe here it's at the center, but here it's not at the center of this area. Okay? So I should not subtract it from C2, I should subtract it from CS. So as you see here, I can take area steel as a common factor. So here I have F yield minus 0.85 FC prime multiplied by the area steel. So CS is equal to 60 KSI minus 0.85 FC prime, which is 4 KSI, multiplied by the area steel, which is 4 inches squared. So CS is 226.4 K. So those are the three forces applied on that section. That gives you a uniform strain, that gives you uniform stress. Okay? How much is the force that gives you those forces? It's the summation of those forces, right? So Pn, the nominal force applied on this section that gives you this strain, is simply C1 plus C2 plus CS. So adding them together, it's 326.4 K plus 217.6 K plus 226.4 K, the summation of the three forces. And that's equal to 770.4 K. So what's this going up over here? We said you have an axial force here, Pn, it's equal to 770.4 K. If you have a force that's 770.4 K, okay, it will give you this strain distribution. But again, we found the magnitude of that force that gives me this uniform strain distribution, but I didn't find its location. What's the location? If this force moves to the right or to the left, the strain distribution will not be uniform. Okay? So how to find this x prime? Now, I know that this Pn, okay, multiplied by x prime would give me the moment of this force about this line, right?
You do sum of moments of all the individual forces divided by the total force.
Exactly. This force multiplied by this distance should be equivalent to those three forces, C1, C2, and CS, multiplied by their distance to the same line, okay? Because they should be equivalent to each other, right? So that's what we want to do now. Here, let me draw this here. This was our section. There is a force here, C1. How much is that distance from C1 to that line? It's, it's 3 inches. And C2 is over here. How much is the distance from C2 to that line of reference? It's 4 plus 6, 10. So where did I get this 10? This distance over here is 6 inches, and this one over here is 8 inches. So C2 is right in the middle of the 8 inches, so that's 4 inches and 4 inches. So 4 plus 6 is 10. And then there is a force in the steel, CS. What's the location? It's 8 divided by 4, so that's 7. Where did I get this from? This 7 inches. As you see here, let's go up a little bit. Those steel bars are symmetric, so the force is going to be right in the middle between them. So this is 3 and 5, so it's right in the middle, so it's 4 inches from here, so 3 plus the 4 inches to the center between those two steel bars, so 3 plus 4 is 7. Okay? So I have those distances. So now, Pn multiplied by x bar is equal to C1 multiplied by 3 inches plus C2 multiplied by 10 inches plus CS multiplied by 7 inches. So the distance x bar is C1 times 3 inches plus C2 times 10 inches plus CS times 7 inches divided by Pn. So x bar will be equal to 6.145 inches. Okay? So as you see here, to find the location of the plastic centroid, you needed to find the nominal force first that gives you this uniform strain. Okay? And then you equate the moment of that nominal force, okay, with its components, the moment of the components. Okay? You would be able to find the plastic centroid. In this problem, you were lucky. There was some axis of symmetry over here, so you know that the plastic centroid is on that axis of symmetry. You were just looking for the horizontal distance. If it's not symmetric in both directions, you have to do this twice, taking moment about a vertical line to find the distance x bar, and taking moment about the horizontal line to find the distance y bar. Okay? Any question?
I was writing when you explained the 7 inches. I get that.
The 7 inches is the distance from the centroid of the steel bars to that line of reference. Your steel bars are here and here. They are symmetric. You have 2 bars here and 2 bars here. So the centroid of those 4 steel bars is right in the middle between them, right? So you have the distance here is 3 and 5, so that distance is 8. So the centroid of it is right in the middle, so it's 4 inches from here. So 4 plus 3, that would be 7. Okay? So that example covers how to find the plastic centroid. So that's the plastic centroid. It's at a distance 6.145. So for that column, okay, if the axial force is located at that point at a distance 6.145, then there is no moment, okay, or there is no eccentricity. If Pn moves to the right or to the left, then there will be some eccentricity and there will be some moment applied on that section, and the strain distribution will not be uniform. Okay? If this Pn moves to the right or the left, the strain distribution will not be uniform. Okay? Any question here? Okay. So that's the first example that we wanted to solve. Now we want to solve another example on constructing the interaction diagram. So we said the interaction diagram looks like this. What's the definition of the interaction diagram? It's a diagram, it's a figure, okay, that gives us the relationship between the capacity, between the capacity of the column for the normal force and the moment. Okay? This is the nominal capacity over here. So how to construct this curve? As you see those points 1, 2, 3, 4, 5, 6, we discussed those points last time. And as you see, for all those points, the strain distribution, okay, there was something common for the stress distributions of all of those at failure. The strain distribution is always 0.003, negative 0.003 at one side, and it changes on the other side, okay? If you have point 1 here, the strain distribution is going to be 0.003 everywhere. As you move down that curve, the strain distribution is 0.003 at one side, and then it gets less on the other side till it becomes tension somewhere. And here, this balance point is where the tensile strain in the steel becomes equal to the Epsilon mu, and here it becomes more than Epsilon mu. Okay? So how to construct this or find those points? We're going to use a similar method to what we did to find the plastic centroid. Okay? We're going to draw the strain distribution for each of those points, okay? And then find the force, the normal force, and the moment, that would give me this strain distribution. Once I find the normal force, okay, and the moment, this is the coordinates of that point. The normal force and the moment that would give me such a strain distribution. Okay? So let's start doing this in this example, example 10.2. So in example 10.2, we have a column that looks like this. The dimensions are given. The width of the column is 14 inches. This is 24 inches. And over here we have 3 bars and 3 bars on that side. The cover from this side is 2.5 inches. The cover from this side is 2.5 inches. And those bars are 6, number 9 bars. We're required to plot the interaction diagram for the shown column. For the material for this column, FC prime is 4 KSI and F yield is 60 KSI, it's grade 60 steel. So to plot the interaction diagram, I just need to plot as many points as I can, okay, and then connect them on that curve. Each point is Pn and Mn, Pn and Mn. Okay? That gives me a different strain distribution. Okay? So for the solution here, the interaction diagram is a relationship between Pn and Mn that can be resisted with this column. I need to just plot some points here. The more points you plot, the higher accuracy for that curve will be, okay? So, but you can, there are basic points that you must find. What are those? This point here. The case of, pure column. And that's easy, okay? And what's that point? This is pure bending. And there is a point here, the balanced point. So those 3 points are the basic points. You cannot avoid them. You have to calculate those points. And then any extra point is just, for more accuracy to plot that curve. Okay? So how to plot those points? So the interaction diagram is a relationship between Pn and Mn for different strain distributions. To find points on the curve or on the interaction diagram, assume a strain distribution and from equilibrium find Pn and Mn that gives that strain distribution. So let's do this. Try to find point by point on that curve. So point 1, the first point on that curve, the case of pure compression, only compression. There is no moment. How much is Pm? That gives you pure compression, the maximum compression nominal capacity of that column.
Compression concrete plus compression steel.
Okay, so how to write this? The compression of the concrete is how much? 0.85 Fc prime area gross minus area steel plus the compression force in the steel, which is F yield area steel.
Why did you do it this way this time?
Why did it?
This way this time. Last time you subtracted the area steel from the.
Okay, I subtracted, last time I had F yield minus 0.85 Fc prime area steel, right? It's the same, okay? But this time, I'm not locating the plastic centroid. I already know the location of the plastic centroid, right? So I just need to find the magnitude of the force. That's it, right? So here, we have 0.85 Fc prime is 4 ksi. Area gross, how much is the area of that column? 24 times 14 minus area steel, which is 6 inches squared, plus F yield, which is 60 ksi, times area steel, which is 6 inches squared. So the nominal capacity of that column is 1482 K. And that's the first point. So this here is 1482 K and zero moment. Okay? You only have an axial force, okay, that gives you uniform strain, and that axial force is 1482 K. Okay? Any question? Okay. Let's go for the balance point now. Point 2 is the balance point here. For the balance point, you don't assume the strain distribution. You know the strain distribution, right? What's the strain distribution at the balance point? If this is my column over here, those are the steel bars. By definition of the balance point, the strain distribution on that side, how much is the strain distribution on that side? 0.003. And then by definition of the balanced point, the strain over here is how much? Epsilon yield. So the strain here on the tensile steel, it's tensile, it's tension over here, and this strain is equal to epsilon yield. That's the definition of the balance point. Okay? So that is, how much is epsilon yield? Is 0.00207. So that's the strain distribution. This is how the strain distribution look like, right? Now, I just need to find how much is the axial force, there is a compression force, plus a bending moment that would give me such strain distribution. Okay? How much is this compression force, and how much is this bending moment that would give me strain distribution that look like this for this column. Okay? So how to do this? Exactly as we did for locating the plastic centroid. Just find the forces in each of the components of this column. Okay? And the summation of the compression of those forces will be equal to the compression force, and the summation of the moments of those forces will be equal to the moment applied on that column. Okay? So now, let's look on this column. The concrete. Do you have uniform strain for the concrete? No, you don't have uniform strain here, right? Actually, is all the concrete here under compression, or there is part under tension? Okay, so this part here is under compression. But this part is under tension. Can concrete resist tension? No. So you only have compression force in the concrete in this part. Here, you don't have a uniform strain. You have strain that looks like this, linear strain, from 0 to 0.003. What would you do with a strain that looks like this? Something basic that we did before.
Found a neutral axis of it, I guess.
The strain, no. For strain that looks like this, okay, you would replace the stress distribution with the Whitney stress block. You're going to assume uniform strain, stress, okay? So actually the stress distribution will look like this. That's the stress distribution, right? So I'm going to replace this with the Whitney stress block. (0.85 FC prime). If that distance is C, how much is the height of the Whitney stress block? It's A, which is beta 1 C. Okay? What else? What parts of the section here? So I have this part is under tension, this part is under compression, so there is a compression force on the concrete here. There is a tensile force here, right, in this steel. So here there is a tensile force in this steel, which is equal to the stress in the steel. How much is the stress? F yield. Why? Because the strain is equal to the yield, strain. So this is F yield, area steel, and here there is a compression force in this steel bars as well. Right? So here we have CS prime, okay, which is FS prime, area steel prime, the compression steel multiplied by the stress. This stress might be equal to F yield or less than F yield, okay, depending on the strain over here, right? So the strain here would determine epsilon steel prime, would tell me if this compression steel yielded or not. We did this in chapter 5 when you had compression steel, right? And I have a compression force in the concrete. How much is the compression force in the concrete? It's 0.85 FC prime multiplied by B, the width of the column, times A. This is B, so it's 0.85 FC prime AB. Those are the forces in the component of the column. I have steel in tension, steel in compression, and concrete in compression. Concrete in tension is cracked. I just throw it away. Okay? So now, do you know how much is the tensile force? That's easy. How much is the tensile force? F yield area steel. That's easy. So 60 KSI multiplied by the area steel. How much is the area steel? It's the area of 3 bars, 3 number 9, so that's 3 inches squared. So this is 180 K. That's a tensile force, okay? Just realize that this is a tensile force. To find the compression force in the concrete, it's 0.85 FC prime. You know how much is FC prime. B, the width of the column, you know how much is B. You need to know how much is A. How much is A? It's beta 1 C. How much is C? Can you calculate C? What do you have enough information to know how much is C? How would you calculate C? From the similarity of those triangles, right? You know 0.003 divided by C is equal to that distance, which is that distance, I know how much is it, minus C divided by epsilon u, right? How much is that distance from here to that steel? Which, you remember we called this D before? The width of the column was 24 minus 2.5, so 21.5. 21.5 inches. So to find C, use similarity. You have 0.003 divided by C is equal to epsilon yield. Epsilon yield is 0.00207 divided by C minus, D minus C, 21.5 minus C. Solving for C, so C is, okay, 1 second. So C is 12.73 inches. Okay? Just solving this equation. Okay? Do you want me to show you how to solve it? You just multiply this by this and equate it to this. So 0.003 times 21.5 minus C is equal to 0.00207 times C, and then you solve for C. Okay? So C is 12.73. How much is A? Beta 1C, so it's 0.85 times 12.73 inches. So A is 10.82 inches. So how much is C, the compression force in the concrete? 0.85 FC prime AB. 0.85 FC prime is 4 KSI. A, I just calculated A, it's 10.82 inches times B, the width of the column. How much is the width of the column? 14 inches. So that is equal to 515 kips. Is this a compression force or a tensile force? Compression. So to differentiate between the tensile force and the compression force here, you need to give them different signs. So if this is positive, this would be negative, or the opposite. If this is negative, that would be positive. Okay? So let's give this here a negative sign. So negative means compression. Okay? So now I just found two forces here. I found this tensile force. I found this compression force. I need to find this CS prime. I know area steel prime, but I need to find the stress in the steel here. Is it equal to F yield or less than F yield? What controls the magnitude of the stress? If it yields or not, that depends on this epsilon steel prime. Can you calculate this epsilon steel prime? From the similarity of the triangles over here. Now you know the distance C. So 0.003 divided by C is equal to epsilon steel prime divided by that distance, which is C minus D double prime. Right? So let's calculate epsilon steel prime. So epsilon steel prime is C minus D double prime divided by C multiplied by 0.003. We already calculated C. So C minus D double prime, it's 12.73 0.73 minus 2.5 divided by 12.73 multiplied by 0.003. So Epsilon steel prime is equal to 0.00241. What does this number mean? Compression steel. This is larger than epsilon yield. You're lucky, right? It's much better now. Epsilon yield is equal to 0.00207. So compression steel yielded. So how much is the compression force in the compression steel? It's F yield area steel prime. Why F yield? Because I know the compression steel yielded. What if it didn't yield? What if this value was less than epsilon yield? You multiply the strain by the modulus of elasticity, you find the stress, and that's the stress that you put here. Okay? So F yield is 60 ksi multiplied by area steel prime, that's 3 inches squared, so that's 180 K. Is it compression or tension? That's compression. So that's negative over here. $180. Okay. Now, is there anything wrong that we did? I'm just repeating myself. I just said this sentence a few minutes ago. Yes, over here, this area, I counted this area twice, right? With the concrete and with the steel. Is it concrete or steel? It's steel, so I have to subtract it from the concrete. So how would I subtract it from the concrete? Okay, what I will do is, as we did in the previous example, okay, I will subtract here 0.85 FC prime area steel prime. So that's area steel prime multiplied by F yield minus 0.85 FC prime. Don't forget to do this. The numbers will not be, there won't be huge difference, but this is more accurate, okay? So this is 3 inches squared multiplied by 60 KSI minus 0.85 FC prime, which is 4 KSI. So that would be equal to 169.8 K, and that's a compression force, so that's negative over here. I'll give it a negative sign. So it's not 180, it's a little bit less than 180. Okay? Actually, the compression force in the concrete is 100, the compression force in the steel is 180, okay? But I'm showing it as less than 180 to subtract that from that concrete, okay? Now, my section is divided into 3 parts. Each part can hold this force at failure. That would be compatible with this strain distribution. Okay? How much is the normal force that would give me those 3 forces? How much is the normal force? It's Pn. How much is Pn? You just sum the 3 forces, right? So it's actually C concrete plus C S prime plus T. The compression force in the concrete was negative 515. The compression force in the steel was 169.8 K. The tensile force in the steel was 180 K. As you see here, I use the signs, okay? Those are negative and this is positive, okay? So Pn is 504.6 K. It's going to be in negative, so the negative means it's compression. Okay? So 504.6. So let's go here to the interaction diagram. So at this balance point, this height, this Pn is 504.6 K. As you see, it's less than this value, definitely. 1482, it's 504 over here. But with this normal force of 504 kips, how much is the moment capacity? Okay? How much is the moment? I have those three forces here. The moment of those three forces about any point is equal to the moment of the applied moment on the section, right? The moment of those three forces is equal to the applied moment about any point, okay? So just take the moment about any point, okay, and equate it to that moment, okay? So we're going to do this next time. It's just one step, but we're going to do this next time so that you don't be late, okay? Yes?
Homework due Friday, right?
There is a homework due Friday, yeah.
Can you push that to Monday?
Monday is the last day of the classes, and then you're going to have a homework. The last homework will be due the exam day. You're going to have your exam on Wednesday, right? If you're happy to have a homework on Monday and then a homework on Wednesday, that's fine. Do you want to move it to Monday, but you're going to have a homework on Wednesday, on the day of the exam? So this is
How are we
your
supposed
finished
to-
homework, huh?
I was supposed to know if we did our homework right if it's due the day of the exam.
You have to have a homework on this, right?
Yeah, but how we know we're supposed to do it right if it's due on the day of the exam?
Okay, let's have it due Tuesday, and I will, once you submit it on Tuesday, I will post the solution online.
So we have one due Monday and one due Tuesday?
Yeah. Or do you want it Friday and Tuesday?
That's all, man.
Okay.
I'll go
just-
Friday.
If you want it Monday and Tuesday, raise your hand. Okay.
So
Friday and Tuesday. You didn't raise your hand.
Nobody voted.
No, yeah, I voted.
Okay, anyway, it's up to you. If you want to submit it on Friday, just do that. I will give you till Monday, okay? For that homework. You can submit it till Monday, okay? So before you leave, this is your homework.
Is the final gonna be what is it gonna be over like 7, 8? The final gonna be chapters over.
No, it's not.
Don't say that.
Bad
word in there.
So it's going to be the shear chapter 8, 9, and 10. Okay. Yes. Yeah.
That's why we got ours big, we got our shit. We had PowerPoint. Set up so we don't do it. I actually sent it to Sarah. She did it. And take good math. We don't even know where the page is. Each unit in a turn its foundation stuff. That's stupid. He's gonna fail. 20 times points off automatic. They should have, they should have did that whole.
You should have just realized, this is your last break at all.
If he would've had-
wants to be pushed to the next year.
If he would have had foundations then, he would have. He could have.
So after finishing the like Friday before he left, and then he started foundation.
No, he had a page and a half done. The night that we were all there. Page and a half. I was gonna make sure you didn't leave it in there because I'd take it to him.
Yeah, that's right about it.
Yeah, well, I just don't think he signed out.